Welcome to videos on CMOS op amp. So this is a two-stage op amp. So this is the fourth video on design of a two-stage op amp circuit. So this is a two-stage op amp with Miller compensation. So this CC is the Miller compensation capacitor, and CL happens to be the load capacitance. And we have M1, M2, M3, M4 as well as M5 constituting the differential amplifier, and this M6, M7 will go to form the CS amplifier. So we know that in the previous videos, so because of Miller compensation, the pole which was at P1 dash without compensation has been moved to P1. The pole which was there at P2 dash has been moved to P2 now, and the zero which was there at infinity has been become finite here. So it's on the right hand side of the S plane. So this is the effect of Miller compensation. The dotted line corresponds to the magnitude plot of Bode plot of the two-stage op-amp circuit, and we can see there is a pole at P1 dash and there's a P2 dash with an for an uncompensated two-stage op-amp, and you can see this is a solid line representing the compensated frequency response. This is a magnitude plot, and you can see the corresponding phase plot. The dotted one is the uncompensated, the solid one is the compensated one. So we might have seen that. So with this P2 dash as a pole frequency, we had this dotted as the earlier uncompensated phase plot. We didn't had any phase margin there, so the phase margin was almost zero here, so that's why there is no phase margin. So when we actually compensated, now we can see the phase has also shifted. Now we have a phase margin of sufficient phase margin, meaning upon providing the compensation using that CC capacitance, the phase margin has increased. The increased phase margin will certainly increase the value of zeta, so that we'll have the settling time is reduced now. So that is the entire effort of making this compensation to increase the phase margin. You can see the phase margin was hardly not there without compensation. With compensation, we have a phase margin of this much. In order to find the design for increasing the phase margin, the location of amount of compensation that has to be provided. So let us try to obtain what is the gain crossover frequency for this particular two-stage op amp with the compensation. Now we know that the transfer function for the two-stage op amp after providing the compensation will going to have two poles at omega p1 and omega p2. So this is a shifted pole position, and we know that so there is a zero coming onto the right hand side of this plane, so which is located at gm2 divided by cc. So that is the location of 0. Now since this minus indicates this onto the right hand side, and this plus indicate the poles are there to the left side of the S plane. So that's what we saw in the previous slide here. Now this is the 0 onto the right hand side, and this is P1 and P2, the poles upon providing the compensation. So this is what is the GS into H is the open loop transfer function. So GM1 R1 is the gain of the first stage, GM2 R2 happens to be the gain of the second stage, so which is at DC gains, and this is the location of the representation of 0, and these two are the poles. And we know that omega p1 is given by r1 into gm2 r2 into cc, and omega p2 is given by gm2 by c2, and this 0 frequency is given by gm2 by cc. This is gm2 by cc, this is your 0 location. So from this we can clearly note that so omega p1, this omega p1 is far less than omega p2 as well as omega z. So this is the first 0 happens to be at a low frequency compared to the second. This is the first pole after compensation. The second pole and the 0 is too far away. So now omega p1 is far less than omega p2 as well as omega z. So out of this transfer function, we'll consider only this. So now to find the gain crossover frequency. So that's what we are having. So we are retaining the magnitude as it is gm1 r1 gm2 r2. And since this is too far away and this is also too far away corresponding to the frequency, we are neglecting omega p1 term and omega z term corresponding to the 0 as well as the second pole at gain bandwidth frequency, that is at unity gain frequency, we have only the pole corresponding to P1 will be contributing to the magnitude. So we retain only this term. So we are retaining this term and equating the magnitude to 1 now. Now you can see we are retaining only that term and we are replacing that omega P1. So this is omega P1 now. So we have actually replaced this 1 over omega P1 by this quantity. So that's what we are writing here. So it is S divided by omega P1. So this is 1 over omega P1 and replacing S by G omega. So you can see we are replacing S by G omega and we are writing its magnitude. So since 1 plus this omega GBW, this is gain unity gain frequency. So at a frequency omega is equal to GB, the magnitude becomes 1 here because this is unity gain magnitude, and taking the magnitude here, so corresponding to this omega GB R1 GM1 R2 CL whole square, this 1 is negligible, so that's why I can able to write this as this equation. So there are so many common terms in the numerator as well as denominator. If I cancel it out, I can write the unity gain frequency happens to be, from this expression we can certainly find out the frequency at which the gain is unity is given by gm1 by cc. So that is unity gain bandwidth happens to be gm1 by cc. So now you can see the pole and zero location. So that is capacitance C1 of P1 dash will be replaced by, so you can see P1 dash is actually given by 1 over R1 C1. So R1 remains same for P1 dash also, but C1 is now replaced by Cc into Gm2 into R2 due to the compensation capacitance, and hence P1 dash reduces and moves towards the origin. Now you can see P1 dash is moving from this P1 dash to P1 now. So this is moving because the capacitance C1 is replaced by a larger value. You can see the resistance R2 of P2 dash will be replaced by 1 over Gm2. Since 1 over Gm2 is very small, so since 1 over Gm2 is very small compared to R2, the P1 dash actually moves to the left side. So it is moved to the left side to P2. So this P1 dash moves to the right side, whereas P2 dash moves to the left side here. There is a 0 introduced onto the right hand side of the S plane at GM2 by CC. So this is the location of 0. So this is again due to the compensation. Because of compensation, the poles will move apart, and as well as you can see there is a 0 coming from infinity and it is becoming finite. So let us try to find out the pole position before compensation and after compensation. So here I have written only the circuit corresponding to only. Now I clearly examine the pole movement of P1 dash to P1 upon giving the compensation. We know that the first pole position before compensation is given by P1 dash is equal to 1 over R1 C1. So the first pole P1 is due to the differential amplifier. I have written only M2 M4, which is representing R1, and C1 is the output capacitance of the first stage. So we know that P1 dash is now due to the output resistance and output capacitance, which is given by 1 over R1 C1. Where this R04, R02 and R04, because now R0, instead of writing simply R0 as the resistance, we can also write 1 over R0 as GDS. So this is, if you want to write what is R0 here, instead of writing R0, we can write 1 over GDS. So that's what we have. The P1 dash is given by 1 over R02 parallel with R04 into C1. So that can be written like this. And now you can see, instead of writing it as P1 dash is equal to 1 over R02 plus 1 over R04, you can write it as in terms of GDS. Now here P1 dash is now represented in terms of GDS, that is the transconductance between the drain and the source. So GDS2 plus GDS4 divided by C1 happens to be the pole position. This is actually P1 dash. This is not P1, this is P1 dash. Now you can see this is after compensation. Now you can see we have provided a compensation here. The compensation, this is now Miller capacitance. You can see the Miller capacitance will be written like this now. So because of Miller's theorem, we can write this Cc, which is between which is floating here onto the input side as the gain of this stage. The gain of this stage is actually GM6 into R2. So that's what I'm writing. This Cc, which is there between the gate and the drain, is now replaced between gate and the ground here. The magnitude of this Cc onto the input side is actually gain times Cc. The gain is actually GM6 into R2 into Cc is the capacitance now. Now we actually have C1 is represented, the capacitance at the output of the first stage is C1 plus this. But this GM6 R2 into Cc is very large compared to C1. We can actually write this. So this is GM6 R2 into Cc is far far greater than C1. We can actually replace these two capacitors by only the capacitor corresponding to GM6 R2 into Cc. This GM2 is actually GM6, the transconductance of the M6 transistor. Now you can see the position now has been changed from P1 dash was actually GM1 into R1 into C1. Now it is R1 into this capacitance. Now you can see this is now not C1, it is actually Cc into GM6 into R2. So this is the gain of the second stage multiplied by the compensating capacitor. Now we are replacing this R1 1 over R1 by GDS2 plus GDS4 and 1 over R2 by GDS6 plus GDS7. So we are representing the P1 in terms of GDS, GM and CC. So this is what is the pole position after compensation. This is for the first pole. Similarly, we can look for the second pole position. So this is the second pole position before compensation. This is R2 and C2. And the corresponding resistance of R2 is R06 in pair with R07, which you can write in terms of GDS as GDS6 1 over R2 is given by GDS6 plus GDS7. And of course you can write the gain of the second stage as GM2 into R2, where GM2 is given by GM6 and R2 is R06 in pair with R07. So P2 dash is now given by 1 over R2C2. So 1 over R2C2 can be written as GDS6 plus GDS7 divided by C2. Now this you can easily write it. This is the position of the second pole before compensation. You can see after compensation what happens. After compensation, you can see now we have a capacitance Cc as a compensation capacitor. Let us see what happens now. So now you can see this capacitance which is over here. After compensation, we know that the capacitance will be offering very small resistance. So you can as well represent this by short circuit. If you are representing this by short circuit, now this impedance looking into the drain becomes 1 over GM6. Now actually the pole now after compensation will be this R2 into C2. So what is R2? R2 is no more R06 in pair with R07, because looking into the drain, this capacitance after providing compensation becomes 1 over GM6. Now it is 1 over GM6 in pair with R07. Since 1 over GM6 is very small compared to R07, R02 is actually GM6 only. So that's why this P2 whatever we are writing, which is happens to be 1 over one over R2 into C2 will now become 1 over GM6 into C2. So that P2 is now given by GM6 by C2 or GM2 by C2. So this is the pole position after compensation. I can see the poles have actually moved from P2 dash to P2 and P1 dash to P1. So this is the development of 0. So you can see now here this M6 is now replaced by NMOS transistor just for analysis. Now because of this compensation capacitor, the V out is due to the two input voltages, that is due to Cc as well as due to this input at the M6. That can be represented by these two equations using superposition theorem, so which can be readily written as this way. As you can see here, so because of this compensation capacitor and because of this superposition theorem application, we actually see there is a 0 developed here. So this is the representation of a 0 onto the right hand side. That's why the 0 which was there at infinity without compensation has come to a finite value with this value.